Welcome to another podcast. In this episode, we're going to be taking a look at properties of relations. We're going to start by sort of setting up our definition of various properties. We're going to begin that by supposing that R is a binary relation on the set A, which means that R is a subset of A cross A. And the first property that we're going to define is reflexive. So we say that R is reflexive if for all A in A, so for every value in our domain, the ordered pair AA is in R. Meaning that all matching ordered pairs have to be in the relation set for it to be reflexive. Next definition, R is irreflexive. Now don't confuse this with being not reflexive because it's not the same thing. So R is irreflexive if for all A in A, the set AA is not an element of R. Alright, next is let's talk about symmetric. So R is symmetric means that for all A and B in A, so this involves potentially two different points. If you know that AB is an element of R, in other words, A is related to B, then that implies that B is related to A. Seems reasonable. The next one is antisymmetric. So we say that R is antisymmetric if for every A and B in A, then we have that if AB and BA are elements of R, then A has to equal B. In other words, the only way you get symmetric elements of the relation set is if they are reflexive elements. In other words, A equal A or B or AA or BB. All right. Fifth property is asymmetric. So we say R is asymmetric if for every A and B in A, we have the property that if AB or A is related to B, then B is not related to A. In other words, the ordered pair BA is not in R. A lot of students confuse antisymmetric and asymmetric, or they might actually think it's the same thing. These are not the same. Can you figure out how they're different? 4 and 5 are not the same. All right, sixth property, and this will be our last property, is transitivity. This is an important property. We say that R is transitive if for every A, B, and C that are elements of A, we have that if AB and BC are related, then that implies that AC is related. So basically, if A is related to B and B is related to C, then A is related to C, is basically how you would say that. So these are the basic relation properties. We are going to give a small example now. We're going to give a couple of examples. The first example I want to give is, let's look at the set R. So this is a relation. And we're just going to define it by showing you the ordered pairs that are there. I'm not going to give it a name or anything like that. But 1 is related to 1, 1 is related to 2, 2 to 1, 2 to 2, 2 to 3, 3 is related to 3, 4 to 2, 4 is related to 3, 4 is related to 4. And so that is our relation set. It's a relation on the set A consisting of the elements 1, 2, 3, 4. So we don't have to worry about why is 5 not in there, etc. All right? So it's the elements 1, 2, 3, 4, and this is our relation set, which is a subset of A cross A here. All right, so let's talk about these properties. I'm just going to go through 3. I'm going to talk about reflexive. So is this reflexive? Well, in order for it to be reflexive, I have to have all of the identical ordered pairs in here. In other words, I need 1, 1, 2, 2, 3, 3, and 4, 4 to all be elements of R, and if you check, they are all in there. So this is reflexive. So yes, we are reflexive. Okay, what about transitive? So let's check and see if they are transitive. So to disprove transitivity, remember the way that quantifiers work. R is transitive if for every A, B, and C. Well, the way that we would disprove that is if we can show there exists an A, B, and C. In other words, I'm just going to show you a pair that's not transitive here because this is actually not transitive. If you look at the pair 1, 2 and 2, 3, 1, 2, and 2, 3 are both elements of R, and if R is going to be transitive, then this must imply that 1, 3 is an element of R. But if you look, 1, 3 is nowhere in the set R, so 1, 3 is not an element of R, so this is not transitive. We lose transitivity. Next up, I want to look at symmetry. So is the relation symmetric? In order for it to be symmetric, whenever I see an element in there, the flip of that element has to also be in there. And just like for transitive, this actually is a no as well, and we're going to disprove it with an example. 2, 3 is an element of R, which should imply that 3, 2 is an element of R, but 3, 2 is not an element of R. So it doesn't imply in either of these cases what we actually want to have happen. So 3, 2 not being in there means that it can't be symmetric. So this one is only reflexive. It's neither transitive nor symmetric. Now, I'm not going to go into looking at the rest of the properties in this particular video, although we will talk about them in class. The 3 main ones that we need to be good at in this class are proving transitivity, proving symmetry, and proving reflexivity. Those are the 3 properties that we're going to spend most of our time on. Let me give you just one more example that isn't quite as forthcoming. We got to think a little bit about what's in the relation set here. So the example that I have is we'll define R as being the distance relation, meaning that R is equal to the set of all points A, B in the reals, such that the distance between A and B is equal to 1. So this is all points in the plane who are 1 apart from each other. So if that's how we define the relation, it's a relation on the real numbers. And if we look at that relation, let's talk reflexive. Reflexive means, basically it means, is the distance A to A equal to 1? That's what we have to ask. The answer here is no. The distance from A to itself would be 0, and it's not 1. So you would never have the point A comma A be an element of the relation set R, therefore it can't be reflexive. Is it symmetric? Symmetric would imply that the distance from A to B equals 1 if and only if the distance from B to A equals 1. And that's a good assumption. If we know that the distance between the points A and B are 1, then it doesn't matter if it's A to B or B to A, the distance is still 1. So this is true. It is symmetric. Transitive. Is this a transitive property? Is the distance from A to B equal to 1 and the distance from B to C equal to 1? Is that enough to tell you that the distance from A to C is equal to 1? So is that true? The answer there is obviously not. We know that the distance is less than or equal to 2. So this is sort of like 3 points of a triangle. The hypotenuse is less than the sum of the other two sides, but we don't know exactly that the distance was 1. Could I set up a particular A, B, and C so that this is true? Sure. But remember, the definition of transitive is it has to be true for every A, B, and C. And so if I just pick 3 points in a straight line, and the distance between A and B is 1, and the distance between B and C is 1, then the distance between A and C is not 1, it turns out to be 2. So this is not true in every case, therefore it cannot be transitive. So this is just an example of some properties that we're going to define on relations, and a big part of this chapter is going through and investigating what those properties mean about different sort of real-world applications of relations and how that plays out, A, proving that a relation has certain properties, and B, then applying those properties to a situation. All right, thank you for watching.